a change on the program. The last presentation was anticipated to yesterday. So the place of that will be taken by Sonia to stop Scott from the cutback process, and this will be an online presentation. So I think that we can just get started with the first speaker, that's Anita Weckenhout. I think, I don't know how I did pronounce your name, from the Kumeri project. Please, Anita, we are ready to start with.
Yes. Thanks. Hello, everybody. So I'm going to talk about some limit separations. So we develop, one part of community is the development of a membrane-based process for the re-refining of used lubricant oils. Oh, and it's come. Yeah. I can put moves. Yep. Yeah. Otherwise, I will. Yeah. Okay. So we had already yesterday 2 talks about community projects. So it's all the community project is about resource recovery and also CO2 reduction by using membranes instead of alternative benchmark, typically distillation projects, or not using anything at all. So I'm going to focus on this liquid treatment line, and I'm going to explain you all about it. We have a very nice consortium working very well. Thanks.
Can you try again, maybe?
Yes. Okay. Excellent. It works. So used lubricant oil. We all have it in our cars, the lubricant oils, of course. And in Europe, it's all very nicely collected. And you have this 1.6 million tons collected every year. And about 2/3 of it is refined, mainly by distillation, so very energy intensive, by 27 refiners in Europe. And it gives us, it's about 70% of this base oil that is in there, which is recovered. Now, how does this used lubricant oil looks like? It's, of course, pitch black. We all know this. It's about 70% of the nice brownish base oil, but then you get a lot of impurities inside. And about 10 to 20% of these impurities come from the lubricant additives, which are typically surfactant-like and containing metals. So when using, they collect a lot of other things. They get oxidized, and you get a lot of dirt in this oil. There's also other impurities in the use. You get also water, few percentages of water, diesel, and naphtha in the system. Anyway, the oil is very viscous. You see there numbers, 50 centistokes, kinetic viscosity at 40 degrees. So this means that we want to treat this for efficiency at high temperatures and with ceramic membranes. So the target, of course, is to remove all these impurities and get back the clean base oil, where you can make again lubricant oil from that. So typically, conventionally, this is done by multi-steps. Often a pre-treatment to get the moisture out, and then one or multiple steps of distillation, giving you a very asphalt-like material that can be reused as roofing material for our houses. And often also the last step is a hydrotreatment to get out all the sulfur. Now, we work in this project with a French re-refiner is called Ossiloop. It's actually a collaboration between Veolia, who is collecting the dirty oil, and Total, who is making the new lubricant oil. They use this three-step distillation, first water coloring, then diesel column to remove the diesel, and then the last high temperature with vacuum distillation to remove all this dirt and giving you the asphalt roofing type of material. They're quite big, re-refiner. They don't use hydro treatment, meaning that in their products there is still a little bit of sulfur again. Of course, what we want to do is replace this on top very energy intensive system by a membrane-based system. And in the beginning, we thought, yeah, we probably need some pre-treatment to get the water out. And then we can do a lot of things with UF, ceramic membranes, and then later on a polishing step with membrane extraction. That's what we envisioned. And looking at this, you can really come down with energy even around 90%. We did a preliminary TEA in this project, and this learned us quite a lot. So the CAPEX compared to the Ossiloop system is like 50% lower if we don't need this pre-treatments, and I will show you in a minute that indeed we don't need it. The OPEX is about the same. It's actually defined by the cost of the used lubricant oil. And so they have to buy it from Veolia to treat it further. So in general, we have 1/4 of the cost going down. And we learned also from sensitivity analysis that it best is to have membranes that have a lifetime bigger than 5 years, and you don't have to go to, if you go to fluxes of 5 and above, that is okay. You don't need to be very huge. No. Okay, what we did, of course, in the lab, a lot of testing of a lot of membranes. We tested different pore sizes. You see there from 5 to 100 nanometers. That's different materials. We have Fraunhofer and Rauschert membrane suppliers in the project. And we did also test a lot of craftings, because our idea was oil is a very apolar stream. So if we make our membranes more hydrophobic, it all will go faster and more efficient. So we use different type of craftings. The selenation done by Fraunhofer, and then at Vito we have the Grignard modification, very peculiar crafting, phosphonic acid known in the art, and then we also put small polymer brushes at Vito. We have this system also. So in all, we had, I think, around 40 types of membranes that we tested. Of course, we want to do this at high temperatures, so you see isolated systems there to be able to treat it. What we found is that looking at the fluxes here, that is of course very dependent on the temperature. And the temperature is the main way to increase your flux. It's also very nice to see that it evolves nicely with the viscosity of your permeate, not of your feet. In this case, it's really very different, but it's the permeate which goes through the membrane, of course. We have limiting floods because of all these dirty impurities in there. Around 10 bar is a nice way to process. And we have also some influence of cross flow following actually laminar flow behavior. So we have ways to simulate and to model this system. now, how does the retention look like, the purification look like? And we actually found out that UF does a very nice purification step already. You see here in blue the feeds. In orange, you see the UF effect, and in green is where we want to come, is the product of oscillator. So you see for water content, actually we remove with this very big open pores UF membrane, we do remove the water. And probably this is because the water is complex or coupled to some of the impurities there and is actually bigger. And then also viscosity, oxidation level, nitration level, we nicely decrease, coming very close to where we want to be. Of course, diesel naphtha, we don't remove. As to the metals, you have metals from additives, from fouling, like from sand, the silicon there, or from beer, from your engine, iron, you see there. There's quite a good removal of the metals, but sulfur is not. It is probably very small, and phosphor is also one of the difficult metals. These were results of native 10 nanometer membranes, which we use a bit as a benchmark. But we used, like I said, lots of other membranes. You see actually the polarity of the different membranes we used here. I plotted it using the Hansen solubility parameters. I'm a big fan. So you see here the polar Hansen parameter and hydrogen, and it goes from the native membranes, which are water-like polarity, down to the no polarity at all, which is here in the 0 point is the oil itself. Okay, what you see there is again the permeate quality of the different membranes, and actually there is not a lot of difference. And I can put many more membranes. There is not a lot of difference. Only the flux and the water removal is changing. Also, when you would look to the metals, it's exactly the same picture. So from this, we selected actually membranes that have a good combination of high flux and a good water removal, so that we don't need any pre-treatment in the system. With these pre-selected membranes, we did, of course, the full concentration track. In our process, we want to do a full concentration and go with the UF permeate to the ME, to the membrane extraction. So we tested 6 membranes here, and as long as we keep the cross flow to 2 meters per second, the flux decline is rather nice. And we can even model it. It's consistent with field theory. When we look to the other graphs, to the permeate quality, we picked the permeate samples, of course, at different moments of concentration. We went all the way up to about 70% recovery, which is the maximum here. And we see that the permeate quality stays nicely constant. So, and it's similar for all membranes. Also good to see is your retentate that you create is then very viscous thing. You have to keep your temperature to get it out of your loops. And it contains quite some water, which is consistent with the high retention of the water we have. So, okay, this is UF. The next step is the ME. How ME, it's based, of course, on the selectivity of the extractants. So the first thing we do is look for good extractants. So we tested a lot of solvents on the permeate that was created by UF. And we could even see a nice correlation between the extraction efficiency I put it there for sulfur, but it's the same for other metals as function of the Hansen parameter, polar or hydrogen, total or hydrogen part. So the more apolar, the better it works. Now, we picked out, it's also nice to see if the efficiency is quite well. We also have nice color removal. So you see back the brown color, what you wanted to have of the base organ. Now, we picked out especially 3 of them, ethanol, NAP, DMA, dimethylacetate, it stands for, and these are good extraction efficiency, and anyway, in all these cases, we had a lot of emulsions formed, a lot of phase difficulties to get phases out. So using a membrane in the extraction process is really very positive. So as to membranes, we rely on the silanated, nicely silanated membranes of Fraunhofer and Rauschers, and we typically take 100 to 200 nanometer membranes with a very hydrophobic surface. We tested, we have an experienced partner from Basel, Switzerland in this project, and they have a nice lab setup, and that it's a huge amount of tests here, and you see the good removal of different metals. It's going relatively slow. You see it here with ethanol, but the stability is very well. They tested it over 2 weeks, and we know by now that we can increase this process, the rate of this process, by going to high temperatures. So not using ethanol, but using high borders like the NP or the DNA, and increasing also the hydrodynamics. Now, in our process, we also want to go all the way to TRL7. It's an innovation action community. So what we know that we can go directly with the ULO into the UF, get a good purification there, polish then with the ME, but then we are still left with diesel and naphtha. So we will need a rather simple distillation step to do this last removal, to get back the base oil. And so we've started our piloting in June. Idea is to have 6 months. In reality, we will be a little bit longer. And we use a pilot that we had actually at Vito already before. It's an ATEX pilot through a pump system, typically with a pressure pump and a circulation pump. It's quite semi-automatic. There's a lot of online tracking of the different parameters, and we can work with it. It was designed to be able to work to 130 degrees and do also quite a lot of cross flow. We typically make our pilots actually very, very flexible so that we can use also many different type of membranes. Especially for this project, we extended it with backflush. In lab scale, we have a lab scale backpull system at Vito, but it didn't work very well. So it was, we were very curious to see the effect of the backpulls on the UF part in the pilot. We equipped it with a bigger module. Normally we have like 0.75 square meter. Now we have put 2 square meter of membrane, which is 8 multi-channel membranes of 1.20 meter, and somewhat smaller for the ME. You see the modules there. You see the system when it actually arrived at Vito and was working for the sub tests. So that's the standard, the whole system actually. And here you see the backpulse unit, and we use the backpulse unit also to have the extractant loop for the ME. So we use the same system to do also ME. And the feed part of the UF is then just the feed part of the extraction. And because of this big module, we decided also to have a separate membrane kit. So all the types of membranes, also the ME membrane is there. That's how it is installed at Ossilup. And I think I will show the results, of course, of the pilots. In blue, you see the lab results on left and right. And in red is the pilot results. And you can nicely see we actually completely found back the results that we had at lab. As in view of flux, we worked at 120 degrees. Also, the quality was the same as what we were finding at lab. And then now it was very interesting, of course, to see the effect of the back pulls. When we don't do the back pulls, you see the red crosses there. We actually have the same flux decline as in the lab, but with the back pulls, we can really bring it up, and there is no flux decline whatsoever. Very nice also, we could have long-term stability. We could drain it, start again with new ULO and get the same process again. Different things happened at Oslo, nothing to do with the pilot, but it's really very robust process. It can be shut down even for 24 hours or longer. You get back where you were ended. So I think this is very nice. We are in the middle of the ME piloting, so I will show results later on, of course, on the collected UF permeate. And then, as last step, also will do some distillation steps on what we create after the ME. And then, of course, this will go into updated data and LCA. This was my presentation.
Okay. Thank you. Thank you very much. Unfortunately, we are very tight with time, and questions will be asked during the lunchtime or whatever. So I would like to ask Dr. Abhishek.
Before I dive into technology, gasification, and high temperature, I want to throw some light on why we are doing what we are doing. And I want to touch upon two topics here: the why based on both supply and demand. When I say in terms of supply, I mean in terms of feedstock. So these numbers, if you can see, as of now, we have currently 1.86 billion tons per annum of waste-based feedstock available. And out of it, around 960 million tons is municipal, 580 million tons will be forestry, and around 320 based on wood waste kind of feedstock. And if we use these feedstock effectively, efficiently using gasification, it may lead us to fuel 100 million trucks with 100% green gasoline, around 15,000 ships with nearly 100% methanol yearly, 7.8 million long-haul flights with nearly 100% SAF annually. And also, these are all cases, we can produce nearly 372 million tons of recycled plastic waste yearly. Having spoken about on the supply, let's look into the demand side. So there are two scenarios here. One is about the SAF. In the first graph, I think the graphs are self-explanatory, but if you see, we are currently standing in 2025, where the existing plus announced supply is nearly 6.4 million tons. However, if we move into the year, nearly 2035 is, you see the first real gap, where our requirement, like based on the predictions, will be our existing or annual supply will be falling short of the requirements which we have. And as we grow in the year until 2050, the gap is keep on increasing. Now looking onto the methanol side, today as we speak in 2025, there is already an existing gap where nearly 0.4 metric tons in 2025, which is only 10% of the projected demand we are producing today. So the methanol market is already matured or maturing, and as we progress in the years 2030, 35, 40, up to 50, the gap keeps on increasing. So, which brings me to my next slide, that how can we address this gap? And gasification as a sector definitely will come handy. And among that, I want to specifically talk about HCW, which is high temperature Winkler gasification. It is one of the most mature technologies under gasification. We have a TRL of 9, and the gasification offers fuel flexibility, feedstock flexibility in terms of we can gasify forestry, agriculture, MSW, industrial waste, mixed plastic, hard to recycle plastics. And on the product side, we can produce methanol with the help of Fischer-Tropsch. We can also go into SAF, maritime fuel, and with some gas treatment downstream, hydrogen and heat energy. So the technology offers both flexibility on the product as well as the supply side. Moving on, I want to also briefly talk about what the process looks like, which we are commercializing today. It is this we call a gasification island starting from the feeding line. It has 5 major parts: feeding, gasification, cooling, filtering, and scrubbing, which are part of a primary cleaning process. Feedstock, which is primarily in the form of pellets, which enters into our reactor via the lock hopper ring and a dual screw conveying system, and which enters eventually into the reactor. And it gasifies over here, and part of the entrained dust comes back with the help of a cyclone back to the bed. This helps in improving the efficiency of the system. Typically, the gases which exit our cyclone are in the order of around 900 degrees, I would say, and it requires some cooling. So it passes through syngas cooling, where the temperature drops to around 350. And finally, we have a syngas filter where dust in the order of few microns are filtered with an efficiency of close to 99.9%. These are ceramic filters which we use. And eventually, then we have the syngas scrubbing, where water is used as a scrubber, and we can remove ammonia, HCN as part of this cleaning. So I would say in the end, it may lead to a chlorine-free, dust-free, particle-free, and even heavy tar-free syngas when it leaves the island. And later it can go into syngas conditioning process, which includes secondary cleaning and eventually some end products, which may be fuels, chemical, energy. From our experience, our reactor can run up to 30 bar oxy-blown, and we have a high carbon conversion of nearly 95%, and our availability, which I'll speak also about from our reference plants, above 91%, and we can go up to 1,000 tons per day in single train. Having spoken about this, I want to touch upon a bit of history of our gasification technology. So back in 1920, that was the first time Dr. Winkler introduced gasifier based on Winkler process. And over a period of close to 100 and plus years, this technology has evolved, and with a total investment of more than $1 billion. I would point out some key important, references during the entire journey of how this technology was developed. So in 1970s, Thyssen Group, they developed the first commercial plant in Berenrath, where the input was lignite, MSW, RDF, plastics, and the facility ran for close to 12 years, and we were able to produce nearly 300,000 tons of methanol per day out of this facility. Next, in Finland, we had another commercial facility which was based out of initially peat, but eventually, due to some law changes, we had to switch it to sawdust. And there also we ran very successfully, and we produced ammonia in the order of 250,000 tons per day of ammonia production. Next, so these two facilities were running at a pressure of around 10 to 12 bars. But as part of development, we moved on to high pressure plant, where in Wesseling, Germany, we tested our reactors even at 25 bars, and which successfully ran, and we produced syngas out of lignite again here. Then in Nihama, which is Japan, we even demonstrated our gasification technology using MSW. So waste from homes were used to gasify, and this was integrated with the IGCC downstream for electricity production. As we speak today, we have our with the Darmstadt University as our partners. There is an demonstration or a pilot scale testing unit at Darmstadt, Germany, and it has been running since 2015. And we jointly do a lot of test campaigns together, testing new feedstock, developing for technology development. At this point, I would like to invite my colleague Philip, and over to you, Philip. Please go ahead.
Thank you, Abhishek, for the nice introduction about HEW and Vidara Energy. Now I will close the loop to the project Biomega Fuel. There we want to develop a novel, efficient and scalable process to convert biogenic residues into syngas. Therefore, we want to use chemical looping gasification technology, and the provided syngas from the gasification will then be converted into methanol through a new membrane reactor, which will develop by the TU Eindhoven. And we also do some tests for HEW, that we have a benchmark for gasification that we then can challenge the chemical looping gasification against commercial gasification technology. So here you can see the pilot plant at our facility in Darmstadt. Here we have our gasifier island where all the gasifiers are located. Then you can see here the gas cleaning plant where we are able to remove all the components in the syngas which are not useful for the synthesis. And then we can also test some methanol or Fischer-Tropsch catalysts in a small test rig to demonstrate the whole process chain. In the gasifier island, we have two reactors which we can operate in a coupled way. Then it's either a dual fluidized bed gasification or chemical looping. Or if we run one reactor at standalone, we can make CFB gasification, as Mark yesterday showed his results, or HEW gasification. And now I will focus a little bit more on HEW gasification. What it is, we have the reactor has a height of 11 meters. At the lower part of the reactor, we have a bubbling bed, which is fluidized by CO2 or steam. Into the bed, we add the feedstock, where we have homogeneous temperatures. The feedstock releases the volatiles and the fixed carbon gets converted. For the conversion of the fixed carbon, we need some gasification agents. Therefore, we supply oxygen and steam at two different nozzle levels. And as bed material, we don't use sand or ilmenite as in other technologies. The bed is only the ash and the char from the feedstock. And above the bubbling bed, we have a post-gasification zone where we reach higher temperatures by adding additional oxygen to upgrade our syngas, because in the bubbling bed there are some hydrocarbons formed, which then can crack in the upper part of the reactor. And which temperature we can achieve in the upper part, there we have a limitation. We have to be under the ash melting point of the ash from the feedstock. Otherwise, we get agglomeration and don't have a stable operation. So in the last test campaign, we used waste wood as feedstock. Maybe you can see here some colored sprinkles. And also on the other side, you can see the composition of the feedstock. We have nearly 16% of fixed carbon, which is pretty good for gasification in a fluidized bed. And you can also see we have a low sulfur and chlorine content, which was a little bit strange for a waste stream, but And we had an ash drinking temperature of around 1000 degrees, so we don't want to reach higher temperatures during the test campaign in the post-gasification zone. And now you can see here some results of the test campaign. Here you can see the temperature in blue over the time for the post-gasification zone. Also in red, the temperature of the bed. And during the test campaign, the aim was to variate the steam to biomass ratio and see the influence of to the reactor and also to the syngas. So that you can see here that we can see the stairs for the different steam levels. And you can see at the end of the campaign, we nearly reached 930 degrees in the bed. If we then had a deeper look into first of all, here you can also see a typical syngas composition for a pilot plant. The CO2 share is nearly 50%. It's higher than in a commercial plant because our system is flushed with CO2 for all the pressure ports and also the feeding system. And we also measure then also the CO2 in our gas analyzer. We show it here. We also can subtract the amount of CO2, but the CO2 also, it's in the equilibrium of the water gas shift reaction. So we show here the total content. So if we have a deeper look at the steam to biomass ratio over the temperature we achieved, we can see if we reduce the steam amount which are supplied to the reactor, the temperature increases. By increasing the temperature, also the share of CO or the ratio of CO to hydrogen gets larger. And one also beneficial thing was that the share of methane compared to the variable syngas components, CO and hydrogen, gets also decreased. So a short summary about the test campaign: we had more than 100 of our stable operation. There we used more than 8 tons of feedstock, and if we lower the steam to biomass ratio, we have higher temperatures, we have a higher CO2 hydrogen share or ratio, and we can decrease the methane content. We are still waiting on some analysis from which we take some offline samples, which gets analyzed after the test campaign. And because the results are not available right now, we can't say something about the carbon conversion and the CG so far, but I think in the next months we will be able to do this. And then what we will do at the next at BioMegaFuel, there are also some pilot testing in a 1 megawatt scale for chemical looping. What is chemical looping? There we have 2 fluidized bed reactors circulating. In the air reactor, it's fluidized with normal air, where the oxygen carrier or bed material gets oxidized, and then we get only oxygen depleted air as off gas, and the oxidized bed material goes into the fuel reactor, where the oxygen carrier reacts with the feedstock, and by this the oxygen carrier gets reduced, and we get the syngas out of it, and the fuel reactor is fluidized by steam or CO2. And the reduced oxygen carrier goes back to the air reactor, where it gets oxidized again and supplies also the heat, which is gets free during the oxidation for the reactions in the fuel reactor. During the Clara project, we demonstrated at the first time an autothermal reaction operation in a 1 megawatt scale. Therefore, our colleagues used industrial wood pellets at feedstock and also some pine forest residue. They achieved at a not optimized process condition a carbon coal gas efficiency around 50% and a carbon conversion around 90%. And here you can see a typical syngas composition for this process at not optimized conditions. And now we want to optimize this process in BioMegaFuel, especially for waste wood pellets, and then either we want to use wheat husk pellets or olive pits, depending on the tests in a smaller unit. I think Paco will provide some results in the next talk. And we also want to demonstrate in this test campaign the gas cleaning of the syngas, that we then can say what is the gas composition for the membrane reactor. Thank you very much.
Thank you very much for this presentation. Questions from the audience?
I have a question.
Okay.
Thanks for the presentation. I can understand that when you have a gasifier, basically you can take up different type of feedstock. So in that sense, it's quite flexible. However, then I think it makes also sense to assume that also your products can vary a bit. And then my question would be, what do you expect the range of composition to be, and how would it change based on the type of feedstock that you take in? Because I see that then BioMegaFuel has, let's say, something that comes downstream, the gasifier or the chemical looping unit, and then also that one in a way should be flexible, to process whatever comes out of the gasifier, which depends on the feedstock. So if you could comment on that.
I think the main components of the syngas would be the same, CO and hydrogen, what we also want to use then in the synthesis. And all the other components, for example, some hydrocarbons, which gets removed in the gas cleaning plant. There you have maybe to adapt the gas cleaning plant to remove all if you have the big variation of the content, for example. But the clean syngas should be nearly the same. Only the CO to hydrogen ratio could be different, and therefore we also consider an electrolyzer in the gas cleaning.
Okay, thank you for the question. That was my question too. I have an additional one concerning the olive pits. Do you use pre-treated or as they come from the olive mills?
I think they are crushed but I'm not sure. Maybe Papa knows more about them.
Yeah, I mean, the other bits is just on the class. Just on the class. Later we have a photo and you can see. And also there is a sample. Yes.
Okay,
We have this.
thank you very much.
Maybe just present as some of the overview of the chemical looping classification center and chemical looping classification process. That is the main concept in this project. But as in the previous presentation, Heisenberg to Winkler was selected as a reference classifier. I want to tell you something about my institution. I belong to the CSIC, that it's the largest research institution in Spain. They cover all the different subjects, society, life, matter, and we are around 140 institutes in Spain covering all these subjects. And the institute where I'm coming from is the Instituto de Carboquímica, that belongs to the chemical and technology research in the CSIC. And we are inside the Instituto de Carboquímica, that is a center related with energy. We are a group, the combustion and gasification research group, inside that. We are actually 9 research with permanent positions, 7 PhD students, and 3 technicians. As you can see, we have a big background in chemical looping processes. I mean, we are from the beginning, 25 years ago, so we cover most of the fuels that you can imagine, from gaseous, liquids, and solids fuels, and covering all the different processes, combustion, gasification, reforming, etc. And there you can see some of the milestones that we get through these 25 years. But we are going to center in what is biomega fuel. Biomega fuel has 2 main, as previously mentioned in the speech. It's covering the chemical looping classification coupled with membrane reactor for the production of biomethanol at the ends. This project is a 4 years project that with a funding around 3 million, about 4 million euros, and cover 9 partners from 5 countries, 3 research institutes, RISE, that is the coordinator, IOV, and CSIC, 2 universities, Technical Universities of Darmstadt and Eindhoven, 1 for the chemical gasification demonstration, and Heidelberg also, and Eindhoven University, that is the main partner related with the membranes development, and also for companies that you can imagine that is very important in this type of projects, Kitara Energy, Perpetualness, OneCube, and Blue Wall Technology. But I wanted to explain maybe better, because some of the audience maybe don't know what is chemical looping gasification. Chemical loop, the main advantage of this process is that you can obtain a high quality syngas syngas without any separation. So in this way, we introduce the biogenic residues or biomass with a steam, we gasify, and we give the oxygen for the process is coming from the oxygen contained in the oxygen carrier. So there is no oxygen coming from any acid. In that way, the oxygen carrier is reduced inside the gasifier and sent to another reactor when it's regenerated. Okay, so in this way, we can have at the outlet a high quality syngas, very high quality with at autothermal conditions without any issue. So what improve a lot the economy of the process. all the CO2 is concentrated in the syngas. So if you separate at the outlet, you can even get negative CO2 emissions if you combine with CCS. Also, the oxygen carrier, the material that we are using, has catalytic properties regarding tar cracking. So we get a reduced tar formation inside the process. And also, as we will see later, it's possible to obtain pure nitrogen at the outlet of the air reactor. It's got an advantage from the point of view of the economy of the process. But I want to show you how is the process happening. So if you introduce biomass inside the fuel reactor, first you have to take place the drying and the volatilization, and later the char is gasified with water or with CO2 to produce CO and hydrogen. This CO2 and hydrogen can be burned with the oxygen carrier and so also the volatiles in such a way that to get the needed heat for the production of the gasification. But in this case, you can see here some of the reactions happening, but it's very important what is needed to control in this process. Here, the more important in the gasification process is the oxygen that you are using the gasification. So you can go from a perfect syngas, only containing hydrogen and CO, and if you increase the oxygen that you are using, you can go to full combustion. That's only to produce CO2 and water. And in the middle, you have to know what oxygen is needed to produce the syngas quality at autothermal conditions, because this is one of the reasons that we want to reach. We have the experience that this is around 0.3 oxygen to 4 ratio. It's possible to obtain autothermal conditions in the process. But normally, this is done in two interconnected fluid aspects. But what's happened if we want to move to use different oxygen to full radius? This will be done at changing the solid circulating rate between two. But we have done another novelty in this case that it's possible to control perfectly the oxygen used in the gasifier, but using this amount of oxygen in the air reactor. In this case, all the oxygen that we introduce here is captured by the oxygen carrier to reoxidize, and at the outlet we obtain pure nitrogen at the outlet. Obviously, to have the needed gas velocity inside the air reactor, what we do is to recirculate part of the pure nitrogen. So this control of the oxygen ratio to full ratio is perfect and allows operation at different delta T between the two reactors, allows to production of pure nitrogen at the outlet and operate at autothermal conditions. This type of control, oxygen, has been satisfactorily tested both in CFSC and in TUDA within the Clara project. So this is a method that is very important. Also, I want to tell you what is our experience in this type of chemical looping gasification. We have experience from different projects, from national funding, from Clara, and also for another European project related with the Marie Slobodka Curie project. We normally use two different installations, a small one and a 20 kilowatts unit. Later we will see more in detail. But what we have done is to test it different oxygen carriers, both synthetic and mineral ones, and also different type of biomasses from pine woods, some that are very relevant in Spain as olive stone as you can imagine, and almond cells, pine woods, etc. And also in the 20 kilowatt unit, but in this case, the ocean carrier selected with ilmenite, and we get more than 400 hours of operation under steady state conditions. This is a summary of just an example of the result that you can get when you do chemical gasification processes. The main operating variables obviously are temperature, dosing to fuel ratio, and the steam to biomass ratio. Obviously, the most important one is the oxygen to fuel ratio that you are introducing. Here, the operating where we fix is the single chill, mainly the coal gas efficiency, and you can see that the carbon conversion, biomass conversion, and the CO2 capture. That means that is the CO2 that is collected in the fuel reactor, in the syngas, is in all cases higher than 90%. We expect very good results also in this project. And we did a comparison of the different ocean carriers from the synthetic to the minerals at different scales. At the end, what we obtained as result is that obviously the synthetic ocean carriers gives a higher single yield than minerals and weights, but obviously they are more expensive to be used in big installations. And methane is always produced in this kind of processes. This comes mainly from the volatilization gases that is produced in the fluid bed, and is the main factor affecting the single yield. If we can convert fully convert the methane, we will get very much single yield. And also we did some experiments with torrefaction, with torrefied biomass, and we get some improved performance in the gasification process. But just coming back to what we are going to do with the experimental part of this project, this relating work package 2, that first we have selected the biogenic feedstock. This was based in the availability in Europe, and also for not only the availability in terms of production, but also in having in the correct particle size in form of pellets. Later, we did a characterization of this feedstock. The previous talk was related with the pilot testing in the high temperature winkler, and we are mostly focused on the testing in the chemical looping gasification in CSIC, and later, based on our results, the TUDA will do the experiments in the 1 megawatt unit. After that, after selecting the fuels, we are going to do also the kinetics determination, the classification of the selected feedstock, and the modeling and validation of the two processes. At the end, all this we will do inside the project, the techno-economic assessment and life cycle, etc. Here I want to show you some of the scheme of the installation that we have. This is a small installation. It's very versatile, and we need just only 2 kilos of solids inventory. So this unit is very useful for us to determine the behavior of different oxygen carriers that we want to test it. But maybe the more relevant is this unit that is a 20 kilowatt unit. Also, it's very flexible, but in this case, the operating, we are using the fuel reactor as a turbulent fluid bed, so that is closer to what's happening in the largest units. In this project, we are going to use ilmenite as associating carrier. Ilmenite, all the people that knows chemical looping knows that ilmenite is the winner, the associating carrier, both in combustion and gasification. I mean, it has been used at a scale even at 3 megawatts units in the CHIPS project. And normally this mineral is used mainly for titanium production, but in this case, we discovered that it's very good also associating carrier. It has a particle size that we normally use in a fluid bed is between 100 and 300. They have a very nice associating transport capacity and physical properties to be used in a fluid bed. So this is what we are going to use. Related with the feedstock selection, I mean, in this project, we wanted to use bioorganic residues and waste. And so we cover all these 5 different sections, and we wanted to use at least one corresponding to each one of the different sections. So in the case of bioorganic residues, the waste wood type B is going to be used in the 4 installations, the 2 at CSIC in the Hedgeberg Winkler. Previously, we have seen some of the results obtained on that, and also in the 1 megawatt unit in Dastat. Related with the agricultural residues, we are going to use olive pits and buckwheat pellets. And depending on the results that we obtain in Spain, we will select one of them to be used in Ciudad, because in Ciudad they are going to use only 2 of these feedstocks. Also, we are going to see what's happening with the biomass, with the spruce tree-tops and branches. And also in the core of the project, it was mandatory to use microalgae as a feedstock. So this is what we are starting to use in our installations in the form of pits. And well, here we can see the different feedstocks analysis. Maybe there are all of them quite similar. I mean, you can imagine the volatiles content is very high, reduced as content. Maybe the more difference is the microalgae that has maybe more acids and especially highly nitrogen content, as you can imagine. And yeah, we will see what's happening. I just only wanted to show some very, very preliminary results with the waste wood type in the small installations. As you can see, well, it's just only the preliminary results. And also in this project, it's very important to use not only steam, but also CO2 as management. So we are going to test what's happening also in this process. Just to finalize, this is a summary what is already done. That 3 tasks is already done. We are ongoing the task 2.4, and the rest of the process will be in the future. So thank you very much for the attention.
Thank you very much.
Good morning. My name is Harjo Ibowo. I am a part of Unicor. You have seen some of us yesterday, and today I'm just gonna introduce us as a whole. Maybe you have seen that yesterday, Dr. Mara joined on here and Dr. Frederick Osler presenting 2 different things about char and about mild combustion. And here today, we're going to see how they come together in Unicor. And this was supposed to be delivered by our project coordinator here with the yellow frame, but he's in another topic. So here I am. Well, let's see. This is how they come together. Maybe we could see how they are divided and organized. The first one is going to be work package 1 on pyrolysis, which is going to be the conversion of biomass to syngas and biochar. I should mention that first. That is the product that we expect to get from this project. And the second part, some of you have seen yesterday, delivered by Mara, is the mild combustion and reforming. And these whole process will be modeled with the pyrolysis modeling and kinetic modeling. And Dr. Frederick Osler is in charge of this part, porous carbon material. We take care of the solid part of the biochar. This is actually also my scope, this project. And this whole thing will be analyzed using LCA. And the whole project is going to be supported by project and portfolio management activities, which I really don't know about before. But let's have a brief look at them. The first one is pyrolysis. They have some tasks there, writing a survey, pyrolysis study itself, and the integration with mild combustion. I just want to briefly mention that maybe one of the things that we do in this thing, like this is STEMS and Lund University. STEMS have a lot of experience in pyrolysis. Lund University combustion physics have a lot of experience in laser diagnostic. So we combine them and we have laser diagnostic and pyrolysis. That's probably one of the things worth mentioning. Since we don't have any presentation about this here, I'm just going to give you one slide about a little bit about how they are. So we used what is known as a Raman spectroscopy. We modify it a little bit. So now it's a cavity enhanced Raman spectroscopy. It's basically a multipass Raman that can analyze all the phases, but for now we're using it for the gas phase. And we found it's pretty good. It's in good agreement with MS, and we can use it for online measurements, quantification, and so on. And maybe this is for now. And the second part is mild combustion and bio-oil reforming. You have seen, some of you have seen this yesterday with Mara, so I'm not going to go too deep into this, but mild combustion itself uses this greasy cyclonic burner with some special properties. You could ask everything. And work package 3 and 4 concerns modeling. As we have seen before, they're going to model the whole process. They are divided into a lot of parts. I'm not going to go too deep into this, but basically it's going to be mostly kinetics of the pyrolysis and reforming. And the porous carbon material, or the biochar to be simple, has been presented by Frederick Osler yesterday. Some of you might have seen it. Maybe the one thing we can mention about this is that we use neutron diagnostic that can see inside the material. We can do bulk analysis for things like chemical composition and things like 3D image of the inside of the material to see elements or compounds inside the material. And this is going to be supported by LCA. I think it was also mentioned this morning, I think by JR, that our portfolio is low TRL, and it's kind of difficult to do thorough LCA at this stage. So for us, we divide it into two kind of parts. The first is kind of an early LCA that we're doing now, but the full LCA cradle to gate will be done after we get more understanding of the process itself. And work package 7 and 8 are portfolio management. I don't think I have enough knowledge to talk about that. So let's just jump into what we have done so far. We have done Aspen modeling to see how those parts work together. This is, well, the schematics, as you would say. This is the biomass. We model it using the components to resemble pine sawdust. And you have seen it in just the presentation before this, actually, that we can use a thermochemical conversion process for a lot of different feedstocks. But we start with this pine. It's the biomass that is abundant in Sweden. Good enough reason to start with that. And then we pyrolyze them here using, well, I don't want to go too far into it, but we use CSDR because they're really good at modeling biomass degradation. And then the gas goes into mild combustion up there. It's typically when you think about pyrolysis, you most of the time discard the gases because there's not much use for them. Like it's very difficult to utilize them. But with mild combustion, we can use them. So they're going to be going there to power the reforming of the bio oil here. So the bio oil goes here, and the energy from the pyrolysis gas will be used to reform the bio oil into syngas. So this is we're also making syngas, just like the previous presentation. It's just a different path, I guess. And the solid part is here. And we do biochar activation for use in soil amendment. This is where you've seen a lot of carbon in the cycle, but this is where the nitrogen management in the portfolio takes into account. We could either use the biochar to supply nitrogen to the soil or use it for soil nitrogen overabundance control. You can use it to like reduce leaching in the soil and so on and so forth. So this is how we model the whole process. And from here, we could see some things that we would otherwise have to spend a lot of time and effort if we do it experimentally. And we have done some verification and they're pretty good. I think like the difference between the model numbers and experimental result was like less than 6%. And the results has been published in this paper down here. So using this model, we then go into some analysis that we can do early on. This is the carbon balance, and it's kind of complex right there. But you could see some of the key findings there. We could see that according to the model, up to 65% of the carbon ends up in the product, which is syngas and biochar. And we try to maintain easily utilized syngas with hydrogen and CO ratio of 1:1. Well, one downside to that, according to this model, is that we will get coke formation. See about how to take care of that. Coke can be utilized, but you need further processing to do that. There's the carbon sequestration potential up there, 27% or 40% if you then activate the carbon. And the next one is energy balance. We can do energy analysis of the process with this as well. Happy to say that most of the available energy is directed to the syngas production. It will end up in the product. Hasamedin, who is in charge of this modeling, warned us not to get too bogged down in the numbers. But for the next point, I have to say some numbers. The fifth downside is that from this default configuration, the LA3 of the syngas we have is only around 13.4. It's kind of low for syngas because we have a lot of nitrogen in the pyrolysis itself when we use nitrogen as the carrier gas, and in mild combustion when we use nitrogen as the diluter for the oxygen, because it's a mild, low to medium oxygen dilution. And then, according to the model, we need external energy to make this process run. We need other energy inputs. And there is some burn off here, which can be used because there's no energy, but it needs further processing. So learning about those things from the model, we try to do a little bit of modifications. The first thing we tried was to convert the dry reforming, and maybe I didn't get the chance to explain it before, but we aim to do thermal reforming. The thermal. It was like, I think one of the checkboxes in the portfolio call to reduce the dependence on critical material, including metals. So we go for completely thermal process. And we went to dry reforming. But what if we change the dry reforming to steam and dry reforming? Should get more hydrogen, which is actually pretty easy because all you have to do is not dry the tire oil before you put it into reformer. And we found some good things when we do that. We eliminate the coke, we increase the portion of the energy in the products. And in the ideal world of the model, the system can be self-energy sufficient when we use burn off gas and recycle them. Will that happen in real life? Most likely not. But I think one lesson we can learn from this is that we should not ignore the side or waste streams from the process, because then you could consider them and you could process them. And apparently they can provide a non-insignificant improvement to the process. And then we'll play around a little bit more extreme. If one day we need to change the name of the project from Minicore to Oficore by changing the mild combustion to oxy-fuel combustion, we can even get more. We can increase the syngas LE3. I shouldn't say, but it's like around 17 now, something like that. But we will need a lot of different things for that, because now you replace the low oxygens with basically pure oxygen. So you need an oxygen supply unit. It's new electrolytes and so on. And this will increase the energy requirement by quite a lot, like 20%, I think, according to the model. And if we even go further and we recycle everything, there's the burn off CO, there's the hydrogen from the electrolyzer that it wasn't considered in configuration 3. Use them all, we can increase the syngas yield because we need more energy for that. And so this model, even though you can't really say that these are the numbers we're going to get, they teach us a lot about the behavior of the system. That when you increase this, what things goes up, what things go down, and that's going to be very important for us as we go forward. This project, I think, started work late 2023, so we are just in our second year, and there are still a lot of things to be learned from this process. But that's why we do it, and this is what we learned so far from the model. That the process is flexible. You can play around with the parameters, for example, to get different qualities of syngas and biochar. Wow. Oops, actually that's point number 2. Okay. So, and also in the end, we can evaluate the process's ability with different feedstocks, different biomass, or even eventually waste, maybe MSW, like the previous presentation has mentioned. And in the end, the goal is to have this process to be integrated, integratable, is that a word, with other seasonal energy storage system, so it can play its role, aim to take over the world, but at least we can contribute some things to it. And that is the end of my short presentation. Thank you from all of us. And just like we say thank you in different ways, we have different approaches, different methods, but we hope that that can give us comprehensive and robust outcome for this project. And maybe in that case, I would like to extend an offer to provide you with your unique perspective for this project. We'd like to hear what you have to say, what you think about it. Maybe now, maybe at lunch, maybe online. That's my email right there. Feel free to email me. And we would like to acknowledge the EIC for their funding. Thank you. Thank you.
Good. Questions? Yes, please.
Mario, for a nice presentation. I want to understand, because your end goal is to maximize syngas as part of this whole process you are developing. And you're developing, like you have divided the entire process from biomass to pyrolysis and then taking part of oil again into lean combustion. So what is the advantage of this over gasification, which happens all together, let's say in one reactor? So,
You can say like gasification of one box, this is a lot of boxes.
yeah, exactly.
One of the goal we try to meet is multi-product production, and in this case, it's going to be the syngas and the biochar, which is because in this specific call, you need to have like CO2 and nitrogen management, and we achieve that by using the biochar in this case soil management, which help with the soil nitrogen management. So the, I would not be able to offer you energy or material utilization comparison, but this process was designed to meet specific goals, and this is the way we do it. So I'm sorry, I cannot go more into this.
You were at the very first project, but yeah, it'll be interesting to see.
One of the, I don't want to say also, the characteristic of the gasification is that you get mostly ash. It's like you get more gas moving. But that is something we need to do to be able to fulfill this other objective.
I have a question about biochar. Did you characterize the biochar for their metal content according to the feedstock? You envisage any potential application as a biocatalyst or something like that?
I think we have done some metal characteristics by chart, but if you don't mind, I would like to check with Rob.
Yes, the moving stems carry out elemental analysis and all the characterization that can identify the position, let's say, the metals present in. Because it is a very relevant point also for further applications, also for catalytic effect of that, because one of the potential, as Jairo said, we are at 7 year, we are 3 years more to develop our studies and let's say adjust the whole process. And one of possible utilization among many of biochar within the process is, for example, its catalytic effect on bio-oil dry reform, for example. And this is a very relevant point for metal presence in the biochar.
Sure. Okay. There are no other questions. Thanks again for the presentation, and we move now to Jose Ramon Galan Mascaros. Yes. He will tell us about Superval project.
Chairman, for the introduction, giving us opportunity to present our project Superval. That is a European Innovation Council funded project, and it's part of the CO2 and nitrogen portfolio. In the portfolio, the idea is to tackle some of the problems and challenges in the circularity of the nitrogen and carbon chemistry from the industry to the end users. And this is a representation of all the different projects that are tackling this different situation. And you can find here Superval, which is mostly dedicated to flue gas and its valorization. So for those that were present in the panel this morning, this is just a summary again of our ideas of taking the whole challenge for flue gas from its capture. So we are going in Superval project to capture flue gas and to separate it into a nitrogen end that will go to ammonia production, and the CO2 end that will go into a photoelectrochemical device that will produce formate as the carbon added value material, and then with the hydrogen that it's always a side product in electrolysis, sorry, with this hydrogen and the nitrogen, the final aim is to produce ammonia. So you can see that this is a modular project, and one of our challenges, we can use only non-critical raw materials, and I will talk a little bit about how we are going to develop it. So this is the Superval. Hey, welcome, Superval. This is the Superval team, and this is a picture of some of the participants, and these are all the institutions that are playing a role, and I will talk about their contribution to the project. In terms of geography, you can see that we are combining Southern and Northern Europe. So we have Spain and Italy on this end, and then we have also the Netherlands, Denmark, and Germany contributing to the proposal. So as I mentioned, this is a modular project. First module, how can we capture flue gas? This is a problem. Has been solved industrially, because the content of flue gas of CO2, and this was presented by Stefano yesterday in the talk, is very low. So this is very costly. And here we have the team doing the magic to produce this separation. So this is our magic material. In the sense, it's very versatile. It's a MOF. It's a MOF made of copper and a ligand obtained from a natural amino acid. Just a small, in parentheses, comment. It's chiral, so it may have interesting properties for other applications. But as you can see, these are the isotherms. It is kind of selective to the CO2, and it has been also modeled by the team of Sofia Calero and Susan, that we'll talk about it later, how this separation works. It's a material that it's scalable. Here you have one batch, 10 kilograms preparation. For us that we are chemists in the lab, this is very impressive. We always work with milligrams, so, and it can be pelletized, and yesterday Stefano talked about it can be really pelletized, and here you have how a bed of these pellets can separate. This is a breakthrough curve in a synthetic mixture mimicking flue gas, how all other components of flue gas exit the bed very fast, and then you can get CO2 accumulated, and then to extract it with a very high purity from flue gas, 10% CO2 in this case, to 99.9% in just one step. So this is how this material is solved. The stability, we know, Stefano and Santiago ran over 100 cycles with a good reproducibility and stability, retaining over 95% of the original performance. And this is scalable not only as a material, but also in actual devices. And now Orchestra, the company working with this MOF, has a pilot plant working in a multi-liter per minute continuous performance. So once this first part is solved, let's go to a second part. And in this case, we are going to the photoelectrocatalytic device. This device should use solar power as power source, and then water and the CO2 capture to do CO2 reduction and water oxidation. And then we will have a second capture, and it was also mentioned, to purify again the hydrogen from this PEC device, and it will be a unit made with the same MOF, the same principles of the first unit. Looking at the photoelectrocatalytic setup, we have also three challenges, which is the photovoltaic part and then anode and cathode. And this is how Superval intends to solve this problem. This is the electrocatalytic team with especially led by Messina, and here we have Claudio and the rest of the team, and we have Felipe, which is from Tarragona, but it's also working in this area. And well, how are we going to try to solve the CO2 reduction to formate? We have here several challenges to minimize the CO production, because CO is a gas that it's difficult to deal with. We are going to maximize the formate to get maximum efficiency, but also hydrogen is going to be utilized later. So it's not that we want to suppress hydrogen production. We are going to get a good balance. So the idea of Messina team is to use variations of copper sulfide. Copper sulfide, they have been preparing different syntheses of this material with different also aluminum incorporation into the mixture. And here you have some preliminary data that they have achieved for this task. And you can see that depending on the potentials, these kind of materials get potential windows where actually the formate to hydrogen ratio is about 2:1, which is something that we are expecting. And you can see that the CO production is almost negligible, below 0.1%. That was part of the challenge. And then depending on the synthesis, they can really play with this kind of ratio of materials. So one important thing is that for CO2 reduction in electrochemical conditions, you cannot play around much about the water electrolyte. It doesn't matter. You cannot work in an alkaline pH because the CO2 bubbling is going to reduce the pH. You shouldn't work in a very acidic media because then hydrogen evolution is going to dominate because it's kinetically faster. So the optimum conditions for CO2 reduction are typically bicarbonate buffer and a pH close to 7. So now we want to oxidize water, as I mentioned, and this is the work of Felipe Garces and Gazzale at ICIQ. If you want to work with these conditions, you cannot use typical metals. Typically, for water oxidation, you are going to use metal oxides. In these conditions, pH 6, 7, most of the metals are dissolving under an applied potential. So most of the devices use iridium oxide, which is expensive and scarce. So how can we solve this instability due to the pH of the metal? Well, instead of oxides, we may use coordination polymers. In this case, this is Prussian blue. The idea is that the oxides are unstable at low pH because the proton is attacking the oxo bridges and breaking the metals. Here, there's no oxo bridges. This material with cyanide bridges, again, is perfectly stable down to pH 0. But is it a catalyst? Well, a long time ago, we disclosed that the cobalt iron Prussian blue is a good water oxidation catalyst, but cobalt is a critical raw material. So for this project, we couldn't use cobalt. So we started to investigate the rest of the series, substituting cobalt. And surprisingly, we found out that the all iron Prussian blue, 300 all material is actually giving a good performance. Here you have a comparison of a chronopotentiometry. The cobalt derivative is still the best, but iron is very close and particularly interesting, very stable. So this is very promising, and we think that this is solving the two parts of the electrolyzer. So for the PV, we need to reach currents that are not very high because this is the target to match the performance of the solar cells with the device. and we look at the cathode and anode potentials. So we will need a cell potential a little bit below 3 volts. And the idea is to use perovskite cells, but perovskite cells still contain some critical raw materials. One is silver, and this can be substituted. But one more important maybe is the ITO, indium tin oxide. So this is the group of Svetlina Merzanova at Jülich Center. The idea was, okay, let's try to use FTO instead of ITO. And they have been working on this kind of materials, doing the perovskite cells. And of course, to reach 3 volts, we will need a series of solar cells. It cannot be a single solar cell, and they are working in improving the performance. They are reaching good factor fields and a solar to current efficiency over close to 20%. They have better results now, and they show, Svetlina showed these results yesterday, but this is a 3 months old talk. I didn't get these new results, but the idea is to construct a series of these perovskite without critical raw materials devices that can reach the voltage we will need to run the performance. Okay, to end up, we need to make some ammonia, or this was the challenge. We got the nitrogen from the flue gas and the hydrogen from the photoelectrochemical device, and now we are going to use a photocatalytic reactor. In these conditions, this reactor, this is the work of Hermes Garcia and Josep Albero at the Universitat Politécnica de Valencia. And what they are working with are, this is the setup, this is the support, which is this kind of calcium phosphate called hydroxyapatite, and they are working with introducing molybdenum and iron as dopants in this structure, and they are working in these conditions at 300 degrees, 1 bar under irradiation, and they are reaching about close to 20 micromoles per gram per hour. And the next step will be to optimize this catalyst, but also to use this kind of reactors where we are going to have the flux of the gases that we have obtained in the other 2 modules, and then with a quartz window to reach, this is the target, to reach about 500 micromoles. We are a little bit far away, but we have 1 year to go. We will see how the project ends. So this is the overall experimental parts of the project, 3 modules that are going to be combined, but the project is not only about experiments, it's also about understanding. And we have 2 groups doing theory to understand and optimize these processes. On one end, we have Luis Lopez taking care of the catalytic parts, particularly electrocatalytic and also photocatalytic to help us to improve the reactivity. And then Sofia Calero and Susan Goyer, sorry about that, and Susan will talk this afternoon about how they are calculating the diffusivity of gases through the MOF. And I think this is very important. Look at these plots. These are the experiments, breakthrough experiments of the separation of a mixture of gases through TAMO, and these are the simulations. They are developing a program in silico that can tell you how the separation of gases through a MOF will be performed. And this is a very powerful achievement, because if you can avoid all the testing to separate gas or liquid mixtures through a MOF, then it's going to be, I think, revolutionary, not only for carbon separation, but for many other separation industries. And in addition to computation, we also have, and it was mentioned this morning, we have an LCA team, it's Martin Rufi from LCA 2.0, and they are doing the analysis, and Laura Gonzalez from Bareser which is a company in Valencia working with waste management and this kind of circularity and sustainability, and this is also part of the project. So that's all I wanted to share with you today. This is our team. Please, you can sign for our Superval newsletter. You can follow us in social media. And let me end by thank you, OneCube, our host and the organizers and Mr. Sherman and everybody else for your kind attention. Thank you very much.
Thank you very much. Professor, presentation. We go now to the last presentation by Sonia Zoitowska. Are you online?
Yes, I am. I hope you can hear me today.
Okay, yes.
Oh, that's already good.
Sorry, I need to try to.
Okay.
Okay, so today I would like to talk about the carbon nitride material, which we are working as a part of the CATART project. And I would like to show you that we were able to coat the carbon nitride in the act of the photocatalysis for water splitting, and we are now working on CO2 reduction. But before I will go to the main result, I would like to introduce you to the carbon nitride field. This is a quite big field of the materials, which we can divide for beta carbon nitride and graphitic carbon nitride materials. We are here in Max Planck Institute we are working mostly with graphitic carbon nitride material, which we then divide them by a heptazine-based and triazine-based material. My main focus of today's presentation, and actually the main focus of the CATART project, is on heptazine-based graphitic carbon nitride. So here, this one. And why is that? Because this material is built only from carbon and nitrogen, it's free for any noble metal, it's relatively cheap as a catalyst, it's chemically stable, can be reused, absorbs visible light, and as you will see further, it can be processed via CVD method, so we can obtain films or different type of membranes, depends actually what we wanted to do for which type of application. The field is big because within about more than 20 years, carbon nitride has been applied for very different type of photocatalytic transformations, from organic photoredox reaction like here amination reactions, some oxidation reactions in bulk form, but also as you can see here in those two works, we were able to use thin film of carbon nitride coated directly on the vials to make simple oxidation reactions and also fluorination reactions. But carbon nitride in bulk form was also proved to work for CO2 reduction in his mesoporous form and also in the nanoporous graphitic carbon nitride form. But like in any type of materials, we are facing a lot of challenges and gaps in the research. The challenges we can divide it mainly by the 4 different groups. First of all, the first challenge is related to electronic structural behavioral changes during the photocatalysis. So now we are trying to check what are dynamic band edge shifts, what are the charger combination pathways, and of course we are facing challenging in situ characterization. Carbon nitride absorbs visible light, but it does not have very good cover during the entire visible spectrum. So we are trying to narrowing the band gap and preserve the redox potential. Therefore, we are coming to doping strategies or some hybridization with sensitizers. Another quite important issue to solve is related to stability and reusability. We know that the carbon nitride can structurally degrade over the cycles. We observe some surface changes and some intermediate accumulations, so we're trying to develop some surface modification strategies. And finally, scalability and producibility. We observe batch-to-batch inconsistencies, especially for the bulk materials. This can be solved by using them in the film form. Some synthesis protocols are very not unified. The scale-up is not very intuitive. And of course, here we are trying now to introduce the machine learning to avoid all those issues. And owing to those challenges, we decided, as I mentioned, to use CVT technique to obtain the thin film of carbon nitride to work with that in the in situ characterization during the water splitting. So on the bottom, as you can see, we prepared the film using the gold substrate, which gives us very good conductivity. We use melamine as a precursor and classic CVD technique. So we have two heating zone tubular oven, where in the first zone we put the precursor melamine, and in the second zone we put the substrate. In this case was the gold chip, and we heat first substrate to 550 degrees Celsius. Then subsequently we heat the precursor to 300 degrees Celsius to avoid sublimation, and thanks to that we form the beautiful film, very flat film on the surface of the gold, and also visibly you can see the change because the substrate changed from the gold to that color. And those samples we used to we sent, and we went together to synchrotron facility in Lund, where we were trying to use operando atmospheric pressure XPS, trying to answer the question, how carbon nitride surface oxidation state change under the reaction condition during the production of hydrogen. We wanted to know which exactly species occurs on the surface, how they can be detected, and can we improve the understanding of the reaction pathways during hydrogen evolution? Because from what was known until actually last year is that technically carbon nitride alone without co-catalyst shouldn't be active in the water splitting reaction, but in a few slides I hope I will prove you otherwise. So to prove that the film which we obtained is indeed carbon nitride, we perform also basic characterization of the carbon nitride film, so we can see the typical absorption spectra of carbon nitride with the typical optical band gap around 2.7 electronovolts with typical spectrum, typical PL spectrum. Moreover, we see also from the FTIR spectrum characteristic features confirming us that this film is indeed carbon nitride. And the film thickness we prepared was approximately 16 nanometers, measured thanks to AFM, where we simply make a scratch on the surface and then make the AFM imaging. And those samples then were used to perform operando atmospheric pressure XPS characterization during the flow of heavy water to perform the water splitting reaction. But here on the top, you can see the typical XPS spectra of the carbon nitride film. You can also see the valence band XPS showing that the HOMO level is around 1.6 electronovolt, what is typical for the carbon nitride film in the ultra high vacuum condition. But what happened when we flow the heavy water into the system? We use with pressure of 0.2 millibar. And after flowing the water, during the flowing the water, we were measuring again the XPS spectra. And you can see that the absorption of water shift the XPS features of nitrogen core level, carbon core level towards higher binding energies, especially for nitrogen, which the nitrogen plays a role in the donation of electron density to form a hydrogen bond with heavy water. This behavior lowers the entire electron density of the surface layer of the semiconductor, and that's why we also see the shifts of the carbon core level features towards higher binding energies. Important to note is here that we couldn't measure the signal coming from gold, so we can exclude the gold precipitation in the entire catalytic process. We see those pronounced shifts, especially for the nitrogen features, also when we follow the NEXAF spectra. But as a consequence of the donation of electron density to form the hydrogen bond with water, we also saw the shift of the valence band XPS position towards higher binding energy for around 1.04 electronovolt. And in the simple terms, we can say that the water precipitates in the formation of the joint new hybrid semiconductor structure with carbon nitride, which results in a different electronic structure than the one we know from the ultra-high vacuum conditions measurement. And this band shift, as we know, was never actually discussed before. And this is indeed the first step to activate artificial photosynthesis. And those are the electronic properties of carbon nitride which precipitate in the photocatalytic reaction. But what happened when we will shine the light to the system? So we use solar simulator. And after shining the light, we see that the carbon nitrate obviously absorbs the photon and excites the electron from valence band to conduction band, and localizing them most probably on the water absorption sites they are the most electron deficient. And this added photoelectron density can be visible in the shift of the core level features towards lower binding energies for nitrogen core level as well as for carbon core level. And this shift points us that we form some stable species, like here, nitrogen photoelectron deuterium or nitrogen deuterium oxygen carbon, and those species are stabilized by the conjugation over the carbon nitrate structure. On the other hand, it must be noticed that we don't see significant differences on the next subspectra. Actually, the most significant change is observed in the carbon K-edge restricted area, and probably show us the pivotal role of this particular feature in this step, photocatalytic step. And also, if we take a look and compare the valence band XPS spectra, we can see slight shifts towards lower binding energies because at that moment the surface has slightly lower oxidation potential. We interpret those spectroscopic reflection as a rather stable structure which support the proton-couple electron transfer mechanism of hydrogen formation from water. And this is indeed photocatalysis caught in the act. What we are only missing here, we are missing the faster, kinetically faster Hall transfer, presumably from the carbon side to the rebound oxygen of the heavy water. However, here we were working with quite particular conditions, 0.2 millibar of water. We wanted to know, is there any pressure dependence? Will we be able to observe the same changes if we will increase the water pressure? And here you can see the XPS spectra of nitrogen core level and carbon core level at different pressures of water together with the valence band XPSs. And indeed, we can see that for the higher pressures, 1 and 2 millibar of water, we observe multi-layer adsorption that cause smaller shifts of the edge functionalities towards, of course, higher binding energies, because we assume there is a weaker electron donation. On the other hand, valence band XPS show the shift to a higher binding energies, like you can see here, from 2.6 for 0.2 millibar of water to 2.8 for 1 and 2 millibar of water. That suggests us reduced surface electron density at higher water pressures. However, in the study of the entire catalytic process, important question arise, which was, will it be possible to get the carbon nitrate back to its original properties? So if we will desorb the water, we will be able to obtain the same electronic signature. And this is what we did. So we performed the desorption by simply evacuating the measurement cell until ultra-high vacuum conditions, and we kept the sample there for approximately 1 hour. And after that, we measure again the XPS spectrum. But surprisingly, for after vacuum desorption, we observe negligible changes for N1S core level. However, for carbon core level, we observe shift towards higher binding energies, which suggests us that probably the removal of loosely bound water further depletes the surface electron. And moreover, valence band narrows from 2.6 to 2.8, which shows us very stable carbon nitride water interaction. And also it seems that when we're trying to make cycles, the carbon nitride and the second cycle, its electronic structure will be different, and then it might behave slightly differently. But in our entire system, we had the TOF MS in the downstream, so we were able to follow the products during the reaction. So we were following signals from deuterium, heavy water, deuterium, and oxygen. And as you can see here, upon illumination with the solar spectrum, here is the block marked with yellow. the signal from deuterium decrease with also slow increase of the signal coming from deuterium and oxygen. We wanted to confirm if it's the thermochemical character of the process, so then we turn off the solar simulator and still perform the measuring, and you could see the increase again of signal from deuterium for heavy water and slow decrease signal from deuterium and oxygen. But indeed, we prove formation of deuterium and oxygen during the catalytic process. So in general, we can say that light absorption induced overall electronic system reduction, and it shows us the signature of the localized electron photocouple, which is integrated in the surface. And the photo-generated Hall transfer results in the formation of surface-bound hydroxyl radical, which is stabilized at the carbon side by the spin component of the localized photoelectron. And after all those results, we were asking ourselves how we can now use the same catalyst, so again carbon nitride film on the gold substrate, and use this knowledge to transfer it and try to make the CO2 reduction, which is a key reaction in our project. So in general, we started from understanding the information about the CO2 reduction, which we already have. So we know that the process requires several steps, from absorption of light, the charge separation, then the diffusion of the charge to the surface, and finally the reaction. We know that the CO2 reaction occurs at the conduction band, but we also know that from the solar fuel perspective, it's important to form not only CO, but actually more like methane, methanol, glycerol, ethylene. And to form those like high energy density products, there is need to have a multiple sequential proton and electron transfer process. So we have to understand the mechanism in general, the kinetics, how the charges are separated, and the absorption activation behavior of the material to be able to get better results. And that was our key point in the next study for the CO2 reduction. So we wanted to determine optimal reaction conditions. Here we were working with CO2 and hydrogen mixture in the gas phase. We again use atmospheric pressure XPS to track the surface bond, intermediate, and reaction dynamic in the real time. We wanted to examine the material alteration, try to develop the mechanistic understanding, which will allow us to make the rational design of the next generation of the carbon nitride photocatalyst. As our ultimate goal is now to enhance the efficiency for artificial photosynthesis. And our very preliminary study showed us that we are going in the good direction, because if we look at those XPS spectra here on the top, measured, of course, in the ultra high vacuum condition, and then on the bottom measured when the mixture of CO2 and hydrogen in this condition was flowed, we see again the signature of the adsorption, because if you take a look on the carbon level spectrum, we can see the shift of the features towards lower binding energies, and also formation of two new species, adsorbed CO2 and also CO feature. On the other hand, there are very negligible changes in the N1 level XPS spectrum, which gives us the clue that here the carbon species plays important role in the first step of adsorption of CO2 on the surface of carbon nitride. Of course, we also notice small shift of the valence band XPS towards lower binding energies. But what happened when we will shine the light? Then, as you can see from the here bottom spectra, that we observe again shift of the carbon levels towards lower binding energies, with decrease of the population of the feature associated with CO2 adsorbed species, and increase the population of the CO species. That suggests us that indeed CO2 reduction or some reaction of the CO2 occurs on the surface of the carbon nitride. And on the other hand, here we also observe small shift of the N level features towards higher binding energies, and we assume that the photo-generated holes are localized on the nitrogen species, and they are of course increasing the they are increasing here, shifting features towards higher binding energies. Important to note is that we were also using TOF-MS located at the end, at the downstream of the entire system, and we were able to track the signals coming from CO and methane at that moment, but that was the very preliminary study. We didn't make any quantification. We will do it in the next step of the research. So to sum up my presentation today, I can clearly say that we can successfully apply CVD to grow homogeneous and uniform carbon nitride films directly on the desired substrate. We also discovered that the absorption of water and CO2 change the surface electron density and electronic properties of the photocatalyst. We can track the interaction of water and light, and as well as CO2 and light with the carbon nitride. That comes with very specific spectroscopic signature, and each functional site contributes to each step. And of course, regarding the CO2 studies, we are actually still working on that, and we are focusing now on discovering the full mechanism pathway. What is the dynamic of the intermediate species, and what is their influence to the electronic structure of the carbon materials. So I would like to finish my presentation and acknowledge, of course, the CATART project. You can visit our webpage to see what we are doing and what the entire network is doing in the project. Of course, I would like to acknowledge Max Planck Society for the support, and with the representation of the CATART, I would like to thank you for your attention.
Okay, thank you. Question from the audience? Very short one and very quick because we are out of time.
And instead you saw the hydrogen and oxygen signals appearing, which means that the reaction was actually taking place. But do you have any values of conversion about the water, like how much water you are converting?
We were trying to calculate it, and it was around 15%, but we were working with our XPS specialists, the beamline specialists, and we didn't publish those data numerically because we don't know how accurate they are, but on our level, it was around 15% what we calculate.
Okay, thanks.
Okay, that will be very nice now to load metals on that carbon nitride and see what happens. So thank you very much for your presentation. Let's thank all the speakers of today.
Thank you very much.